Welcome to this HPC Architectures lecture on advanced CPUs. Although advanced CPUs is a little bit of a misnomer as a name for this lecture, because really we're not talking about very new or modern processors particularly, and we're not talking about processors that do things in a different or groundbreaking way. What we're really talking about is some of the functionality and some of the hardware that have been added to processors over the past 10 or 15 years to address performance issues and to address functionality and usage by manufacturers of processors and its functionality which you wouldn't have seen on processors 10 or 15 years ago. So I guess we're talking about advanced functionality for processors, things that have been done to processors above and beyond what you could think of as individual functional units or individual functionality of the processor. And a lot of this is in response to things that we've already discussed in the course, things like the fact that you can now manufacture very large numbers of transistors for an individual processor or individual bit of silicon, but that doesn't necessarily mean you can actually put that all together in one single processor because of physical limitations about things like how far a clock signal can propagate across the electronics in a given time. And also very much some of this functionality we're going to talk about is in response to the memory versus processing performance gap, which we've talked about already. You've gone into much more detail in the memory and cache lectures, where we identify that processors have got much quicker and memory systems have not got quicker at the same rate, which means that nowadays it's much faster to process a bit of data, to do an operation, an add or a subtract or something like that on a piece of data, than it is to load that data in from memory to a processor and do the work on it and store it back out. And actually a lot of the functionality we have in modern processors is built around mitigating this performance problem. So caches are built around trying to get away from the cost of loading data up by storing data you've recently used and storing data which is located close in memory to data you've recently used in faster memory, which is located closer to the CPU and which you can access from the CPU in much shorter amounts of time and thus get better performance. And we've been through this. You should have already been through this in the cache lectures in this course, so have a reasonable understanding of this. But it's worth bearing in mind that to get good performance, large amounts of processor area are set aside for caches, and that uses quite a lot of the silicon. It also uses quite a lot of the energy and produces a lot of the heat which goes into and comes out of the processors. So there have been pushes in the past by manufacturers to try and produce hardware which doesn't need caches, to try and produce other ways of getting around this memory gap, this memory performance gap. And that's going to be the first set of functionality we're going to talk about, the multi-threaded, highly threaded processors. And that's still going on today. So for instance, the Xeon Phi, which you'll hear more about in the next lecture, it's an Intel accelerator-based processor. It uses multi-threading, that we're going to talk about to try and hide some of these memory performance issues. Then later on in the lecture we'll talk a little bit more about conventional multi-core processors and what they're doing and why we see them as well. So, whilst what we've already talked about, we have this memory performance issue, and if your program, a given program which is running on a processor, has done a load operation, so it said I want this bit of data to do some work on it, and that data is not in cache, it's in main memory, then it's going to have to sit and wait for that data to get loaded up, so it's going to stall. Okay, now for conventional processors, this is a hit you may just have to take. You just have to wait for your data to get loaded up, and then once that data is loaded up, you hope that you're going to reuse that data and reuse data that's close to it. So it may cost you a little bit at the beginning, but you shouldn't see too much of an impact on your processor. But there is another approach that you could take with processors, and that's to say, well, if this program which is running, this application, this process which is running, is waiting for data to come in from memory, could I run something else on the processor instead of it whilst it's waiting, and then when its data arrives, I can put it back on the processor and it can keep going. So it will still have taken however long it took to load the data in from memory, but whilst we were waiting for that, we ran something else useful on the processor, so the processor was being used and it wasn't sitting there being wasted, doing nothing, spending electricity to do nothing. So this is the idea behind multi-threaded processing, or strongly multi-threaded processors, that what they aim to do is try and hide this memory cost, this cost of going to main memory and getting data from it, by running more things on the processor than you normally would. Now, unfortunately, this is not possible with standard processors, and that's because the actual cost of switching between one running thing on the processor and another one, switching between different threads, switching between different processors that are running on a processor, takes quite a long time. So on a standard processor, this context switch by the operating system to say stop running this, now run this instead, takes a long time, thousands of cycles maybe, and that cost is just as long as your main memory costs, your cost of going out to get data from memory. So if we're trying to switch things out to hide the cost of main memory, but the actual process of switching two things on the processor costs the same amount, it's not going to help us at all. And that's primarily because when the operating system does a context switch, when you switch over a running process, you have to store things into memory and you have to load other things back up from memory, and that means it can take a long time. Okay. However, you can, with addition of some small amounts of things to the hardware, you can actually switch between running things very quickly. So with hardware support, you can switch between running threads in a single clock cycle. You need to add a little bit, you need to be able to have multiple registers files so you can store the data that thread was using somewhere on the processor and whereabouts that thread was in its program. But if you have that, then you can switch between running threads, running things quite quickly, and that means that if one thread that's running stops because it's waiting for data to be loaded in from memory, you can quickly start something else and let it run until it stops and waits for something to be loaded in from memory, and then you can run something else, and then you can run something else, and that way what you hopefully you're doing is you're getting many things running on the processor, and that means that at any given time the processor is busy doing some useful work. Of course, for an individual application, an individual program or an individual thread, it still will have to stop and wait for its data to be loaded up. But across your process, across all your running programs, you're not seeing the same cost because you are utilizing that CPU usefully whilst something's waiting for data to be loaded in. Okay. And there are different ways you can handle this. You can just say each clock cycle I run a different thread. So each clock cycle another thread gets a chance to do an instruction, and we just keep swapping through those. You could say run a given thread until it gets to a point where it stalls waiting for data, and then run another one, and then run another one. And you can do something where in between where you say run each thread for 10 cycles until one stalls and then run the next one, that kind of thing. And there have been relatively recently processors and hardware with this kind of functionality built into them. So Cray designed a custom processor, the XMT, which was a highly threaded processor, 128 threads per processor, and it had no caches in it at all. So it was really pushing to the extreme of saying if this multi-threaded works overlapping compute and memory accesses and hiding the cost of memory accesses, then we can get rid of that cache altogether, and the fact we're not using the cache in the processor should make them cheaper to manufacture and cheaper to run. Does that give us a good performance benefit? One of the downsides, of course, is that it requires your applications to have some parallelism there, some numbers of threads in there, so you can have many things running at once on the processor. So the Cray XMT could run up to 128 threads per processor, and that means if you're using your application on this machine, on this processor, you probably want your application to be able to generate a large number of threads to be using that processor for your application. Okay. Otherwise, you're going to have one of 128 programs, and 128 other people are going to be using this processor as well, and that isn't necessarily going to give your application brilliant performance. There have been other examples of this. So the UltraSpark T3 also had highly threaded functionality in it. And BlueGene-Q processor, which we'll talk about a little bit more at the end of the lecture, does have multi-threaded functionality in it. And as I previously mentioned, the Xeon Phi, the current Xeon Phi processor, it has around 60 physical cores, and each one can run 4 threads. And actually, for the Xeon Phi, as you'll probably hear in the next lecture, you actually have to run more than 1 thread per core to get reasonable performance on the processor, because the way the hardware is designed, a given thread that's running on a core cannot issue an instruction on back-to-back clock cycles. So if a given thread does a single instruction, then it can't do another instruction on the next clock cycle. You have to have a second thread there that can do an instruction. So the Xeon Phi cores can run up to 4 threads efficiently. To switch between them in a single clock cycle, you actually probably need at least 2 threads to get good performance, but you can run up to 4 threads per core on that kind of processor. So that is multi-threading, and that is truly running multiple different kinds of programs on the processor, but running full multi-threads. So you'll run one program, and then you'll switch to another program, and then you'll switch to another program, and each time a program is running, it will have full access to the CPU until it's switched out. There has been hardware added to modern processors which does something similar but not exactly the same, and you are likely to have heard of it as things called hyper-threading or symmetric multi-threading. And actually, this has not been designed to overlap memory access costs, to try and hide memory access costs. What this has been designed for is, because modern processors generally have multiple functional units, so you may have a couple of floating point units and an integer unit and a load store unit and things like this. So think parts of a processor which can do different bits of work. One bit that can load up data or store data, one part of a processor that can do integer adds or integer subtractions, a couple of parts of a processor that do floating point operations. And because most processors, modern processors, are what's called superscalar, that means that they can issue instructions for more than one unit in a given clock cycle. So you can say, I want to do a floating point operation and I want to do an integer operation in this clock cycle, or I want to load some data up and do some floating point arithmetic on some other data. There is this recognition that most programs generally can't use all those floating point all those functional units at once. So your program is not likely to be able to do integer and floating point and data store and load, all those kind of things at once, because the way the program's written. At some point you'll be doing some integer work, and then you'll do some floating point work, and then you'll go back to integer work, and then you'll store some data, and then you'll load some data, but you won't do all those things at once. You may have dependencies between the instructions, so first you can load a bit of data, and then you can do a floating point operation on that data, and then you can store it again. But you can't do all three of those instructions at once. So if you look at sort of a lot of applications, you could see instruction level parallelism, i.e. can you use multiple functional units at once in a single clock cycle for a given application, is not generally as high as the actual CPU itself supports. So the CPU may let you use 4 or 5 functional units at once, but your program may probably only issue instructions for 1.5 or 2 of those functional units every clock cycle. Which means that actually, in terms of the hardware, you have parts of the processor that are often not being used in a clock cycle because your program can't take advantage of them. So manufacturers think, well, if I have multiple functional units here, not all of them being used, is there any way that we could run more than one program at once and use these functional units and share them between the programs that are running and get them all used at once? And this is the idea behind hyperthreading or simultaneous or symmetric multi-threading. That is that if you can run more than one program at once on the same core, on the same processor, you might be able to use all these functional units at once. Now this, just like the multi-threading example we talked about previously, this requires some extra hardware, so you have to add some extra things onto the processor to support being able to run more than one program at once. So you need to be able to track multiple instruction pointers and registers and things like these. But again, it's not a large amount of extra functionality you have to add to the processor. So you could say about 5-10% extra silicon to support being able to run 2 programs at the same time. Okay. And then that means you should be able to do something like this. In this picture here, we have 2 programs. The program on the left is used, so each one of these columns that you see, it is a functional unit, and then the columns which are filled up by colours are where that program is using a particular functional unit. So you can imagine the first column of the 2 threads could be loading data, and the second column could be integer operations, the third column and fourth column could be floating point operations, and the fifth column could be branch operations. So you can see on the left that the first thread, which is got red colour on the left hand side, on the first clock cycle when you run that program, it's trying to say load some data and doing some floating point operations, and on the second clock cycle it's doing some integer arithmetic and some floating point operations and some branch prediction. And the third clock cycle it's trying to do some more loading of data, for example. And then the second program on the right, on the right there, which is in blue, it's doing different kinds of instructions every clock cycle. So it's starting off doing integer arithmetic, and then it's doing a load and some floating point operations, and then it's doing 2 floating point operations, and then it's going on to doing a load and another floating point operation, for instance. But we can see in the gaps between the colours and the non-colours, well, where there aren't colours in the picture, that's where functional units in the processor are not doing anything, are sitting idle. So we can see for these 2 imaginary programs, there are places where they're both using different functional units on the processor, and if we can overlap these 2 programs, if we're running, then you get the picture on the right hand side where it says 2 threads on 1 SMT CPU. So we can run both programs at once, and because most of the time they're using different functional units, they can end up coexisting, and we can actually run both programs instead of taking 6 instruction clock cycles for each program. We could take theoretically 7 clock cycles, and we could finish both the programs in that. So we can see in this synthetic example, then you get a speed up of almost a factor of 2 times quicker when running both the programs by letting them share the CPU. So this is the idea behind hyperthreading or symmetric multi-threading, simultaneous multi-threading. that you run 2 or 4 programs at once, they share the processor, and they try and use the functional units in a more efficient manner, so all of them are being used at once if possible. And it doesn't use very much silicon to let you do this. And so a lot of modern processors, most of the modern Intel processors have hyper-threading in them. A lot of processors do nowadays. My laptop will have 4 cores in it, but each one of those cores can run 2 threads in hyper-threading mode. So Windows thinks it has 8 logical cores. It actually only has 4 physical cores, but it's doing this hyper-threading thing to share each of those physical cores with 2 running tasks. So in theory, this is quite a nice piece of functionality, and it looks like in theory you should be able to get good performance with it. In reality, it doesn't, particularly for the kind of simulations and applications we do in scientific computing, it doesn't always work out to be massively useful, because the way you implement hyperthreading, I skipped over it slightly, but in this slide we see you add some hardware in to enable support of running multiple threads at once, but actually most of the things you are still sharing between the threads. So you're still sharing the memory and the cache between the threads. So if I'm running 2 things at once on my core, they're sharing this cache, and they're sharing the access to main memory and the memory bandwidth and latency. And also they're sharing things like the functional units. So if I was to take a scientific simulation which spends most of its time doing floating point operations and try and run 2 of them at once, and they're both trying to do floating point operations all the time, well, they're not going to be sharing nicely sharing the floating point unit. They're going to be contending for it. They're both going to be trying to use a floating point unit at the same time, and none of the other units, and that probably means they're not overlapping very much, and it doesn't really help us here. And likewise, they're both going to be trying to use the same cache, so they're both going to be loading up data into the cache which may conflict with each other. They're both going to be using the memory bandwidth. So there is contention on the hardware resources. So really, it really depends on what we do, what applications you're running, as to how beneficial SMT or hyperthreading is. It can be anywhere between, it slows the applications down, so you get performance impact rather than performance benefit from using it, to somewhere between sort of 1 or 1.1, 1.2 times more efficient if you're using hyperthreading. So I don't have the slides in here, but we looked at hyperthreading on large-scale HPC machines for a range of different scientific simulation codes, and at most you could see sort of 10 or 20% benefit for some codes, and for other codes you could see it making your code actually run slower and take longer to complete. If you compare using the same number of cores but having different numbers of actual things running on them. So it can be beneficial, but in general it has doesn't really give you that 2 times faster that you would sort of like if you're properly sharing all the units out between the running threads and effectively using them. There are ways to tweak this as well for some processors. So the PowerPC implementation of hyperthreading included the notion of scheduling for this. So we're not going to necessarily force you to share the core of a processor equally between different programs. We may give one program higher priority use the core than another one, and this could be beneficial in terms of scientific simulation, because you can imagine if you're running your application on a compute node of a big system like Archer, you want it to use that processor all the time, but there are things that are always running on the compute node, like the operating system and the communication libraries and things like that, which will every so often interrupt your program, interrupt its use of the CPU and impact your performance because of it. Now, if you could schedule these onto the hyperthreads instead. So schedule these as using, not kicking your program off the processor, but going onto the processor alongside your program, but give them a lower priority, then that could give you better performance because you don't see as a bigger impact for these other processes coming in and using the CPU. So there are ideas like that which can be beneficial. Another hardware addition to modern processors along the lines of the things we've already been talking around today is that of SIMD vector units, single instruction multiple data hardware added to the floating point parts of the processor. So these are along the lines of vector processors that we have seen in the past. And the idea here is you have a single instruction, an add or a multiply, for instance, where instead of doing that on one piece of data or one set of data, you do it on multiple pieces of data at the same time. So we can imagine, we can look at these two bits of C and Fortran code we have in the slides here, where we've got a loop where we're adding one number to another and storing it into a third. And we're doing this over a large range of numbers, so from 0 to n of these arrays B, C and A. Now in a standard serial instruction you would start off at 0 and you'd add element in the C code element 0 of a B array to element 0 of a C array and store in element 0 of the A array. Likewise in the Fortran code you'd start off an element 1 of a B array, add it to element 1 of a C array, store it in element 1 of the A array, and then move on to element 2 of a B array, add it to element 2 of a C array and store it in element 2 of the A array. Just move on doing this operation one element at a time. However, vector units, these do the same instructions but let you do that operation on multiple bits of data at once. So instead of for instance in the C, starting at element 0, moving to element 1, then 2 and then 3, if I'm going to do using some hardware which has a 256-bit vector unit and my elements in my array are 64 bits, which is what usual double precision numbers are stored as on modern hardware, 64 bits data structures, then I can actually do 4 of them at once. I can do element 0, element 1, element 2 and element 3 in the same clock cycle. I can add B to C and store to A for each of those elements in the same clock cycle. And this doesn't really, again, require very much change in the hardware to support this. You need to have bigger registers to store more data in them. You need slightly different floating point units. You have slightly different adders in there to be able to do it, but that well, maybe not even adders, but you need slightly wider floating point units. But this is all easily implementable with small amounts of additional silicon, and it means that in a single clock cycle, instead of doing one floating point instruction with this floating point unit, I can do 4 effectively. Of course, it does mean that your code has to be amenable to do that. So if we look at this example, in fact, if I was just adding one number to another and storing it in a third, but there was no loop, I couldn't use more than one instruction here in the vector unit because I've only got one thing to do with those bits of data. So even if I've got a vector unit on my processor, I can't use those extra bits of functionality. I can only use one part of it. And likewise, if I'm jumping around in memory, so I'm not starting off at element 1 and then going to element 2 and element 3, but I'm starting off at element 1, then going to element 7, then going back to element 3, then up to element 10, that makes it much harder to do these operations 4 at a time because we have to load in data from different places and store it in the same registers. The vector units are generally designed to load up cache lines or parts of cache lines and work on them, so it's expecting the data that you're doing these instructions on to be contiguous in memory, loadable in cache lines. So a few years ago we had SSE instructions. These were vector instructions on processors the SSE instruction set, and they did vector operations on 128 bits at once. And this is generally two double precision floating point numbers or 4 integers. More modern processors use AVX instructions, which are 256-bit vector instructions. That means they can do 4 floating point double precision numbers or 8 integers, 32-bit integers at once. And actually the next generation of processors will be are already using AVX2 instructions, which will let you do 512-bit vectors. So you can do 8 double precision floating point numbers at once, or 16 integer operations at once. And but of course only if your code maps well onto that. Only if you're looping through contiguous bits of memory and doing the same sets of instructions on those bits of memory. There is also another modern addition to floating point arithmetic called the fuse multiply add, the FMA instruction, which a lot of modern processors have, and this is where the processor can do a addition and a multiplication on data in the same clock cycle. So you can do an A plus B times C or B times C plus A in the same clock cycle. Now, why do we want to be able to do this? Well, if we can do this, then it means we can do 2 floating point operations in one clock cycle, get 2 things done in one clock cycle, so we can automatically double our floating point performance if we can use this instruction. And it turns out it's also quite easy to implement in the hardware. You probably have to have slightly different adders, but it won't add very much complexity for hardware. And it's also beneficial for some other things you want to do. So it makes it easier to implement square root and division functionality in software. So it means that if you include these FMA instructions on a processor, then you probably don't have to include specialized hardware to do square roots or divisions. So from a processor design point of view, it can be very beneficial. You can sort of double your floating point performance and reduce the complexity of your hardware by adding this kind of thing. But from a software point of view, from a programmer's point of view, of course, you can only use a fuse multiply add operation if you are in the same part of the code adding and multiplying data together. So in our previous example where I was adding one bit of data to another and storing it in a third location, there's no multiplying there. So that couldn't be turned into fuse multiply add operation. So I wouldn't be able to get this double floating point performance there. So you can see that there's been a number of things added to processors which give them higher peak performance in floating point operations, higher amount of floating point operations they can do per clock cycle, but only if your code matches well to it. So if you actually have a look at an example, if I had a 2 GHz processor, 16 core processor, and each core had a floating point unit which could process AVX instructions, and each one of those instructions could also be a fuse multiply add, then that means in that processor we could have a peak performance, peak floating point theoretical performance of 256 gigaflops. In that processor, it's 2 gigahertz, the clock speed. At each clock cycle we can do 4 instructions in the vector unit, 4 double precision floating point numbers, so that's 8 gigaflops there. Each of those can actually do 2 floating point operations and multiply and add, so that times it by 2 again. That gets us 16 gigaflops of performance, and then we have 16 cores. So 16 cores, each capable of 16 gigaflops, gives us 256 gigaflops for the overall processor peak performance. Of course, it also lets us say, well, if I couldn't vectorize, if my code doesn't vectorize well, it doesn't match up into these bits of patterns of code which are working on doing the same instruction on consecutive bits of data, floating point instructions on consecutive bits of data, then the most of performance I'm ever going to get out of my processor, this example processor, is going to be 64 gigaflops, because I've got 16 cores, each can run at 2 gigahertz, and each could do a floating point multiply add, a fuse multiply add instruction. So if my code doesn't vectorize but does do fuse multiply adds, then I could get at most 64 gigaflops. If my code does vectorize but doesn't do fuse multiply adds, then I have a potential peak performance 128 gigaflops. And if my code doesn't vectorize well and can also not use these fuse multiply adds, then at most the best performance I'm going to get out of this processor would be 32 gigaflops. So you can see that from a hardware perspective, you can design and implement processors which theoretically have a very high performance. But from a software perspective, an application developer perspective, it means that unless your code does match well to these hardware characteristics, you're not going to get anywhere near the performance that the processor manufacturer states is the peak performance of these processors. But these things are here to stay at the moment. All the modern Intel CPUs and the accelerators and things like that have both vectorization and fuse multiply add functionality in them. The GPUs are heavily built on vectorization units. So if your code can vectorize well, then you're going to get good performance out of these processors. But if it can't, then that becomes a real problem in terms of performance. And then we come to the other end of the spectrum, which is instead of making small additions to the silicon, small changes, small additions of hardware to what there is in a processor to give you better performance for a given part of a processor, say the functional unit, the floating point units. Here we're going to talk about multi-core processors, which is effectively just replicating a whole processor a number of times on a chip to give you a processor with a number of cores in it, which overall can do a lot of different things. Actually, if you look at this from a user's point of view, it's the fact that you have a multi-core chip is probably the multi-core aspect of that chip is probably irrelevant to you. If you're going to do programming, then the individual cores on that chip just look like processors to you, individual processors. So if we go back to the times where you built sort of small scale systems by adding a number of individual processors to a motherboard, say 4 processors in a motherboard, and you had a 4 processor node, then now we have a processor with 4 cores on it, but from a programming perspective it still looks like the same thing. It looks like you've 4 individual processors on a CPU, on a node. The only real difference actually you see programming wise, performance wise, is whilst generally most of the bits of the processor are replicated when you make multi-core processors, they're not entirely individual separate units, so they do share some things. Primarily they share some of the levels of cache. So whilst you are going to make say 4 or 8 or 16 cores on a processor, you're not going to give them all separate caches. You're going to share some level of those caches. They may have separate level 1 cache but share level 2 or share level 3 cache. And we have also seen multi-core processors that actually share other things as well. So now we'll come on to talk about those. The multi-core thing, so I stole this graphic from a tutorial at the ISC conference a few years ago. The multi-core thing has been around for a while now. Actually, in fact, if we go back to our big HPC X system, which ran early in the 2000s, IBM put multi-core processors in that quite early on in their service. But if you start at the top left of this picture, where we used to have processors which had their own cache, then they were connected to a motherboard which had some kind of memory control in the chipset, and you went out to main memory. The first sort of generation of multi-cores were proper, really not multi-cores as we see them now, but actually 2 physical processors just happened to be located on the same bit of silicon. So they still were separate processors with their own caches. They didn't share anything, but they happened to be plugged into the same socket because they were on the same bit of silicon. And then as we move through the evolution of multi-cores, then you start to see cores having their own L1 caches but sharing L2 caches, multi-cores sharing L2 caches and L3 caches, multi-cores with hyper-threading or symmetric multi-threading, so each core has its can run more than one thread on it. multi-levels of cache, and then vector units. So nowadays we're in this scenario where a processor will have a number of cores on it. Each one of those cores can run a number of threads. Each one of those threads can issue vector instructions, which also do fuse, multiply, add. So we sort of have parallelism at the vector and the vector level, at the hyperthreading level, then at the core level. Okay, and if we go back, one of the first, as I mentioned just before, one of the first multi-core processors we saw was one in our HPC system, which was an IBM-based system and used a Power 4 2-core processor, but very much quite recognisable as a multi-core processor nowadays. So one half of the processor, the top left and the top right, have individual processors, and then there was an L2 cache which was split between them. And we see the same kind of things going forwards. Intel Nehalem, it's got 4 cores in there, and then there's a 8 megabyte cache, L3 cache, which is shared between them. Actually, you could split this up so each core had its own 2 megabyte L3 cache, or you could programmatically share this cache between them, so there's a shared 8 megabyte cache. And then we don't need to labour the point, but there are a number of these over the years multi-core chips. There are performance implications, as I've already mentioned, in using multi-core processors. So cores contend for space in the shared cache. That means that things running on other cores may affect your performance because you're competing for the same areas in the cache and also for the same bus to memory. So the memory bandwidth is going to be shared between all the cores. Because there are upsides of being in a multi-core system as well. So if you're doing some kind of parallel program where your multiple processes or threads are running on different cores, they actually have a fast way of communicating with each other. They can communicate with each other through the cache system rather than having to go over some kind of network or through files or something like that. So if you can get the programming right, then you can have fast communications for parallel programs on multi-core systems, because the communication is simply happening in the cache level and not having to go down through the memory bus or through the PCI Express bus to a network card or anything like that. You can just share data through this shared cache, shared memory space that you have. And there are other places, as I've already mentioned, where things may be shared. So AMD's high-performance chip a few years ago was called Bulldozer, and in here, they actually each 2 cores shared a floating point unit. So the floating point unit actually had 2 128-bit floating point vectors in the units in there, where you could do floating point vector operations, as we talked about. So each one of those could run 2 64-bit double precision floating point numbers at once, or 4 integers. And this was shared between 2 cores. So each core could use all of a floating point unit, or they could have half each. And this was done at a sort of software and instruction scheduling level. In practice, it didn't actually really end up making much difference to the performance of parallel or scientific programs we ran on here, but there was this shared aspect to the floating point unit functionality, and actually they could compete, but they didn't really contend for the so if you have the 2 cores and one program was not using the floating point unit, the other program could use all of it, but they couldn't really kick each other off the floating point unit or starve each other. So if they were both using it, then they would both just get half a floating point unit. But this is the kind of functionality we do see sometimes. There's other things that processors do which may or may not affect performance, and actually we tend to mention this one mainly because when you end up measuring performance of programs that are running, it can be problematic nowadays to try and work out parallel performance because modern processors also do something called frequency scaling. Intel call this turbo boost. But the idea here is that the processor, when it's running, monitors how many of the cores are being used and can change its clock speed depending on how heavily it's being used and how much is going on there. So this is partly to try and get better performance, and this is partly to save energy. So processors, particularly mobile processors in laptops and things like that, will reduce the clock frequency if not much is going on to reduce the energy consumption of a processor and then increase the clock frequency when more instructions are being scheduled to give performance. For the processors we use on something like Archer, there's a turbo boost mode which is designed that if only 1 or 2 or 3 cores out of our 24 cores we have on the node are being used. Sorry, this is done on a per processor basis. So we've got 12 cores in a processor. If a small number of cores are being used, then the clock's frequency can actually be increased to give faster performance for those programs that are running on the cores. So operating the base operating frequency of the processors we're using in Archer is 2.7 gigahertz, but it can run up to 3.5 gigahertz depending on what is going on in the processor. So if you are using 6 to 12 cores, so if you're using half or more of the cores, then the maximum frequency will be 2.7 will be 3 gigahertz, depending on current power consumption, energy, and processor consumption. So if the processor is not too hot and it's not using too much energy, it can push the frequency up to 3 gigahertz. But if you're using less than 6 cores, then it can go up to 3.5 gigahertz to give you increased performance. The main reason we mention this is that when it comes to benchmarking processors nowadays, it's quite unfair to run a benchmark program on 1 core, and then 2, then 4, then 8, then 16, then 32, what have you, and compare the performance between them, because on 1 core it's quite often common that the processor will be running faster than if you're using all the cores on the processor. So it can make it hard to benchmark performance across processors nowadays, because they kind of adjust their performance based on what's going on the chip. So having said that, the multi-core nature of processors is largely irrelevant from a programming perspective, there are a number of areas where you may care about performance. Now, this course is not about performance programming. This kind of stuff is covered more in the second semester course that Stephen teaches on performance programming, performance optimization. But when you're doing programming, particularly parallel programming, but not necessarily just parallel programming, scientific programming, there are some optimization techniques where you understanding the nature of a processor being multi-core and the fact you have shared caches may benefit you, and understanding your parallel programming issues may benefit you as well. So these are optimization. A lot of these are optimization techniques which have also been used in the past, not in the multi-core situation, but they can be useful here. So things like cache blocking and data tiling, delaying and holding data. This is the idea of tailoring your program to effectively use the size of the cache you're given, and so you can make changes to your program to give you better performance because you're making sure that your data is staying in cache and being reused in cache, and taking into account the shared nature of the caches and how much you can sort of apportion out to each processor can be useful here. At a shared memory parallelization kind of level, then the fact that your multi-core processor is also a shared memory parallel computer, a multi-core processor, because they're sharing the last level of cache, and the cache coherency is done at the processor cache levels, then you can treat it as a parallel shared memory computer. So there's things like first touch optimization, false sharing optimization, processor affinity. That's binding processors and threads to particular cores to make sure that they stay where their data was initialized in cache. These can be quite useful in terms of getting best performance out of program. But as I say, this is not really the main focus of this course. Just one interesting processor which we have talked about a couple of times that's useful to have a quick look at is the BlueGene-Q processor. So this is a picture of it here. It's reasonably interesting in the terms of it implements pretty much all the stuff we've been talking about here. It's designed with 16 cores. Actually, they manufacture it with 18 cores. One of the cores is set aside for operating system stuff, so it's got its own dedicated core for that. And then there's another core which is designed to cope with manufacturing problems in the cores themselves. So you've got a spare one which can be switched off if there's any problems in other cores. And each one of these cores is 4-way multi-threaded, which means that it can run 4 threads very efficiently. It has 256-bit SIMD operations, and it can do fuse multiply add operations as well. So it is a processor, relatively low speed, sort of low power processor. It's only running at 1.6 gigahertz. But because it can run 4 threads on each of its 16 cores, and because each can do 4 vector instructions and a fuse multiply add, it can get reasonably high peak performance, so 200 gigaflops for very low power consumption. It also has some reasonably interesting cache prefetching functionality in there. So it has a different prefetching modes, which is the idea here is the processor is going to try and get data into cache that it thinks you're going to use next. So the normal mode for this will be stream prefetching, i.e. if I've seen you load up consecutive cache lines from memory, I will go off and load another one after that, so it's already there because you're likely to use it. But it also has this list-based prefetching mode to try and deal with more complex memory patterns. So maybe if it can recognize a pattern that you're loading up this cache line and then this cache line and this, so cache line 1 followed by a jump of 2 cache lines, and then cache line 4 followed by a jump of 5 cache lines, and you're doing that consecutively, then it will load up the data in those orders, and it can learn as it goes on. So it's quite an interesting, primarily because some of these processes were designed with specific problems in mind. So a lot of this cache prefetching work was done in Edinburgh actually, on QCD simulations which have similar work patterns on these. Yes, so that's really all I wanted to say about processor hardware, processor technology. I mean, really you can see all these different parts, these different kinds of functionalities that modern processors had as being kind of a spectrum of different ways of using the silicon and different ways of hiding memory costs, with multi-core at one end being just complete replication of functionality to use more of a silicon, where symmetric multi-threading and hyper-threading, you only replicate small amounts of silicon to be able to use the processor stuff, and then there's functionality in there to try and hide memory costs and improve floating point performance. And how successful these are really depend on the application you're running and the nature of your code. So if you have any questions about this, please do email me. My email address is on the slides. You can also tweet me, and I will get back to you. And the plan is then, but after this lecture, I'm going to put up some questions on the university's Top Hat site, which you can go and answer, both about this lecture, but also about some of the previous lectures in the course. And this is not, so it's going to be marked anonymously. It's not assessing your performance, but it's assessing the performance of a course as a whole, and have any areas which we can improve or change or need to go over again. So if you could fill those out once they're up, that would be greatly appreciated. Thanks.